Okay, so I'm David. I'm the head of the clean room for whoever doesn't know me. So we just introduce this talk. So thank you, first of all, for being here. It's the first talk of a long cycle of talks we will give until June. It will be around 12 talks, and we will introduce every area of the clean room because we are now in a critical transition. We just finished a large investment with the Minatec project, which started in 2016 and ended December last year. And now we are just starting a new one with the 30 chip. So many changes. So we thought it would be a good time to explain you what we did, where we are, and where we are going. So the first talk will be by Xavier Borrisé, the head of the Nanolithography area since 2006. And well, he's a PhD of the university here and has large expertise in all the nanolithography techniques, or NIL, or SEM, ABL, and so on and so on. Okay. So I may not talk too much, but this project is very important to us and will come very soon. So enjoy the talk and the changes to be coming.
Okay, thank you for coming. So in English then, let me introduce first the people. We are 3 people at the lithography area, which is Liber, Albert, and me, which are taking care of the equipment more or less in the order we say here. And okay, this way. So I'll remind you that nanolithography area means that we want to access to see things and to manipulate things at the nanoscale. Okay, so we want to see at the nanoscale, so for characterization, and we want to also manipulate at the nanoscale for fabrication. Okay, and for that, I will give you a very brief background, so we all talk the same language, and then we will review what we have and what we can do. Okay, so for the accessing to the nanoscale, which means from 1 micron below to the nano level, we have 2 ways. One is using particles, and the other is using proximity interactions. Okay, and if we review that with electrons, because we cannot use light, because light gives us a limit of around a few hundreds of nanometers. We have a very nice microscope with a good numerical aperture. Then we use particles, which are smaller. In fact, they are much more smaller. So in principle, if we send particles, focused particles to a sample, there are some interactions. We collect with some detectors these interactions, and then we can see what's happening at this nanoscale. And there is a lot of interactions, and if interaction can give us different information, so we'll see that also because we have different detectors. And the nice thing is that we are no longer limited by the diffraction, but for other things like basically the capability of focusing the beam. Okay, so that is using electrons. If we use proximity interactions, then it's a different approach. In that case, we are going to approach a tip very close to the sample, a very sharp tip. The idea is that if we use a kind of interaction that it's local, that it's exponentially decaying, then if we have a very sharp tip, then most of the interaction takes place at the tip of the tip. So as we see here, so, and then in that case, we can follow the surface. If we are able to keep this interaction or measure this interaction, then we can follow the surface and have information on the surface. And depending on the interaction, it is thermal current, we have electronic states information, the density of electronic states. If it's forces, we have topography, etc., so on and so forth. Okay, so that's more or less the 2 ways to have for characterization. If we want to manipulate, then we use the same. In that case, we somehow increase the interaction. Or in case of electrons, what we do is we use some material which is changing their property to the electrons, which is a resist. Okay, it's the same idea as optical lithography that Javi will introduce you in the next talk. But just to remind you, we have a clean sample, we deposit a resist. This resist is sensible to electronic radiation, not to light. It could be also, and then we expose it. As I mentioned before, we have a focused electron beam. So that means that when we exposure, we don't use a mask. So this is a maskless technique. It means that we are exposing point by point or element by element. This is then a very small technique. Okay. but it gives us a very high resolution. Okay, so that's the main points here. After that, we develop, as we do with optical lithography, and then we have some area exposed to the whatever we need to do later. Okay. Instead of electrons, we can also use ions. We have a system to do the ions. In that case, it's gallium. When we use gallium, what happens is that ions have mass compared to electrons. Then they have high momentum, so they, when reach the surface, they impact and they can remove. So that's the basic idea, and that's what it's in this picture. So we can control very well the dose, so the number of ions we are sending to the surface. Then we can control very well the depth we reach and the geometry we are making. So in that case, we are directly modifying the surface, also with a focus beam. Okay, it's the same idea. We have gallium, and we are focusing this beam to the surface, and then we remove material. Okay, of course, it's not as simple as process. There are also some phenomena associated, like redeposition, amortization of the surface, and so on and so forth. But that's the basic idea. And when we want to manipulate using proximity interaction, basically what we did here in the past, we are mostly not doing now, but it's still possible. It's local oxidation of surface. In that case, silicon. In that case, we apply a voltage in ambient conditions. We have humidity, and then you can use this humidity to oxidize the surface. Okay, and this creates a contrast. In that case, is this oxidized part that we can etch, and we really have a silicon inside that we can use as a mask or simply remove, and have a very nice control of this system to make an impact. So, which is even more slow than the electronic, okay, because it's also serial. Okay, finally, to manipulate at the nanoscale, because all that we talk is serial technique, we have some parallel technique, which is called nano-imprint lithography. Okay, in that case, we need a mask. In that case, we use a mask, which we call a mold, okay, or a stand. Because in that case, what we do is we really put in contact this mold, which has this 3D structure that we want to transfer to our sample. And then this this mold, it's coated with an anti-sticking layer because we are directly contacting to the resist in our sample. And then we apply pressure and temperature in order that the resist is filling all the cavities when they are in contact with our mold. And after that, we cool down and we remove the mold. And if we do it fine, we have something like this. Okay, and that's the main idea. Because this is temperature and pressure, we have to be very careful with the mold, don't break it with the resist and so on and so forth. But the idea is that we can imprint, and here you have to. Okay, so that's the background. Now you know everything that I know from the basis. So now we make a small journey from where we come and where we go. We started in 2001, more or less. Maybe I'm wrong with some of the years. You can correct me. And at that time, the IMB direction decided to promote the activities in the field of nanotechnology. I was not here at that time, by the way. And to reinforce these activities, there was an investment of 6,000 kilo euros to make a new laboratory. Okay, if I'm not wrong, this is the numbers. At that time, I figured out, last least, that Girona was at third division. Let's keep that in. Okay, and this is the laboratory. Okay, that was on the basement. You see, this is the basement of the CNM, but now this is still the clean room for bonding and with Alberto and also with Xavi. So it was smaller than it is now. And in that basement, we had different systems, which were basically an IFM, which we started, an SEM with some attachment, which allows us to create patterns to do lithography also. And this was with Gemma and Cristina, which were the technicians at that time. Later I came and I started with Nano-imprint also with him a few years later. Okay. Also, together with this, we need also some facilities, for example, for spin coating, because we need to spin coat. And at that time, we were not allowed to go to the clean room to do that, just to say, and we had to go to the UAV. And in there, finally, we bought a spinner and a hot plate, and even this glove box, which was for the anti-sticking layer deposition. All this was at the UAV, so we went there, we spin coat, and we came here, we exposed, and then we went there, we developed it there. Okay, but it was funny times. Later on, in 2006, there was ICN2, which created, which still was not created. What was created was ICN and the CN2, and there was an agreement with the institute for various things, for several things. One is to bought a focus ion beam system, which was installed in these facilities and to give service to everybody. There were also some laboratories that were also used by people at ICN here. I remember that in the basement there was one laboratory, also here in the first floor. So we were sharing some space with them. And the focus ion beam was installed here, where there is the current stepper. At that time there was an old stepper that we removed. Then again, because we were not allowed to go to the clean room, we put a wall, so we enter from the corridor, just in case. I'm joking, huh? But that it's true. So we were not going through the main door, but through the lateral door. Okay. And at that time also, Jordi and Liber started with us, because mainly Gemma and Cristina were in their PhD part. Okay, so that was the past. Then in 2008, there was the remodelation of the clean room. There was a batch, and then we moved. Finally, in 2008, we moved to the new clean room in this area here. And just to remind you also, hope you still kept in mind, Girona also moved from third division to second. Okay, so we move up, they move up. Okay. So that's good. And that was the laboratory, and the systems we have in the laboratory until now is still more or less the same. Okay, we have e-beam facilities, a new equipment for that, a new equipment for Nano-imprint, and then we have the equipment we had, the FIB, the SEM, the Nano-imprint, and all the, let's say, the wet facilities. The people, yeah, all of these people. Jordi left also for his PhD. Then Anna also came. Then Anna left for some more higher level activities, let's say. And then Gemma Martin came also for some time. The idea of this laboratory, as mentioned here, it's to give service and self-service. From the very beginning, this was the idea. So we have a lot of people which is using the equipment themselves, but also we provide service, so whatever. And we run CMOS and non-CMOS processes for most of the equipment. Okay. Nowadays, this is the situation of our laboratory. So just, we will talk about this later. So we have some equipments that are operational, but let's say in a critical situation. Some of them they are abandoned, and some of them they are still. Okay, let's review them. The first one, it's Xavier. This is basically an FDM which is modified for doing EV. Okay, compared to the SEM we had, basically it has an environmental chamber which gives us more stability. It has some automatization process also, which we didn't have before, and we have this stage which is interferometric, which allows us nanometer precision on the positioning of the sample. So in that case, then we can make large exposures with stitching fields, which means that we can make larger exposure than we can do before, with a wide resolution. Okay. What else? Yeah, it has more automatization processes. We can leave it running overnight or over weekend, and we have resists for positive resists for lift-off, for etching, negative resists, also with high resolution, which is in that case below 10 nanometers could be. We have resins which are UV compatible, so we can mix and match with them. We have a conductive coating in case that the sample is not conductive, because remember we have an SEM, so we need that we send in electrons, we need to discharge them, and we have even functional resins. Okay. As I mentioned, this is a serial technique. It's a very slow process, but it's also give us some advantages. One of them is the flexibility. Okay. And for that, I show you an example. This is flakes of a 2D material. We make an SEM image of that. After that, we can import this image in our design. We can create a design out of this image. And then we can go spin coat the resist, go back, and then expose at the right place and make the content. Okay. So that's the advantage of a system which is serial, safe, because we have a lot of flexibility to find marks, to positioning, and to design whatever. Okay. On the other hand, also we have the capability of mix and match with optical lithography, which means that as a first process or in the middle or at the very end, one of the things we can do is the evening process. The only thing we need is marks to recognize. Okay. In that case, this is a wafer. In that wafer, if we zoom in, all this is done with optical lithography. Zoom in. All this is still with optical lithography, and all these are marks that we will use, basically, if we go here, for aligning with the E-beam, and the final step, which is creating this nanowire, then we will do it. Okay, so in any case, this is a very small writing time, but because we do it 5,000 times, this would take, I don't remember, but maybe a weekend or something like that. Okay, so the wafer is working all the weekend. Okay. So as I mentioned, this is a very slow process. But it turns out that because we have a very nice stage and a very nice imaging capabilities, we also can do metrology. Okay, so that means that we can go after our wafer is done, we can put it back and we go to the right place and take measurements, or even though we can make large mappings of samples. Okay, and in that case, the people from Reverse now is using it quite a lot, or sometimes, for making mappings of the chips, which is essential for them. And this is the example. They make images, and after several stitching images, which we overlap a bit because they reconstructed. Oh, sorry, we have several millimeters image of the hodge, and then we can go for the next layer and the next layer. So this is how they reconstruct the chip. Okay. So as a summary, remember that this is a lithographic process. So it means that we use a resist. It's a serial process, which is very slow and without mask, but it's very flexible. We can mix and match with optical lithography, and we can do metrology or reverse capabilities due to our independent system. Okay. The current situation of the system is that it was acquired in 2008. It was yearly maintenance until 2019. But after that, it turns that we have to decrease the amount to avoid the tender. So it's after 50,000, we need a tender, and the price for the maintenance increased. So we didn't agree, or we didn't match. And after that, there is no maintenance. Only repairs that we have done, several of them. So the system is now in a critical situation. For example, the low lock, it's in a manual mode, which means that only Albert and we can load the sample. The users cannot, because it's quite a critical process. There are no replaced parts for that. We are in this, nowadays we are in the restricted support mode, which means that they provide support, but they cannot guarantee that they have replacement parts. Okay, and in the next year, it's finishing the support of the system. So that's the situation. Okay, with the Nano-imprint, which is the other system, we already saw the process. We have the mold that we have to make somehow with the beam or the optical lithography with any other technique. We can imprint from small samples to wafers. And just two examples. One is using lithography. this was from the Nerea thesis, which they make these nanostructures or nanoparticles, which develop shape and composition. It was a process. We did the imprint, then we did the etching of the resist, then we did a sputtering or evaporation in order to tune the nanoparticle shape. Okay, so that was a process. But also sometimes what we do is a direct embossing process, which means that we have a layer of material, like a sheet of material, which is polymer, typically can be PMMA or any other, and then we imprint directly on this material. So it's not a resist. Okay. In that case, this is something we do for the people at the Hospital de Bellvitge, which they ask regularly to make these patterns where they culture these glia cells for their experiment. Okay, and they need this pattern, which is very simple, but it's necessary to imprint PMMA for that. Okay, so that's the Nano-imprint. And so in that case, just remember it's a parallel fabrication with a stamp. So it's lithography or direct with hot embossing. It's no alignment process possible. So it means that it's one step only. So you cannot align with that system. And we have to prepare this one. Okay, it's a sticky layer. So the situation is that there is no thermal maintenance for this equipment. It's quite simple. You only change the oil time to time. But because this is also a very old system, they are restricted. We ask them, but we are limited somehow. Okay. Behind the lithography, also there are some people that is coming because we have a spinner, we have a vacuum oven, we have an optical microscope, and there's a lot of users which are coming for depositing either for graphene transfer or for block copolymers deposition, or just to inspect them on the optical microscope. So remember that you can do that. So that's also facilities that we have and that are heavily used. Okay. Then, if we continue in 2010, we had we bought a second. In that case, because there was a high demand for that, but we saw that many experiments were outside of the clean room. So it was not necessary another SEM inside the clean room. So then we started with a second SEM, which is this one, which was bought in 2010. First we were here, and now it's the optical group laboratory. Then we moved here, where the SEM laboratory is now. Well, now it's SEM only. And finally, after the remodelation of the basement, now we're here with the new FIB that we bought in 2021. Which is from this Minatech project that ended last, okay? And we will review that. So, remind you, as an SEM, we have these two systems on the clean room. This one is the old one that we have, which we used for lithography at the very beginning, which is this part here, which have basic topographic detectors, and we can load up to 4-inch wafers. And then we have this one, which is the old FIB. At some point, the FIB didn't work anymore, so that's why we bought a second FIB. But as an SEM, it's still working, and now we are using it. In fact, the Leo now is not working, so we only have this one. And this one allows 6-inch wafers, has the same detectors plus a current detector. And because it was the FIB, we had some micro manipulators that we use it for making lamellas, but also we can use for making electrical contacts. We have FIB through, so we can make electrical contacts inside and explore the cell. Okay, so the SEM just remind you that it's basically imaging. Okay, and also then we have outside the clean room this system, which is the Auriga, which have the same detectors plus an X-ray detector, which allows us to detect materials from position. Okay, that's also important. And here also we do voltage context measurement for the people for traverse, which is basically exciting the circuit when we are imaging. Okay. The EDX allows us to do a few things. Basically, it's materials detection. In that case, we detected the hafnium oxide and the silicon oxide in different places. So it's in a single point. But also we can do mappings. In that case, for example, we can detect different materials, and after some time, we have these views, which are the materials and where they are located. Either spectra and mappings. Okay. Then finally, with SEM, we have a high resolution up to the nanometer in the best case. We can put almost any sample from chips to wafers. In case of insulating samples, maybe they need to be prepared. Sometimes we coat it with carbon, which is more than enough. And we have different detectors, basically topographic detectors and X-ray detectors. Okay. And remember that the images are always 2D grayscale. So that's not a real image. Okay. The current status, also as we do those. The SEM is already out of service. We are trying to see if we can solve that, but we have a problem with the stage. That there's a power failure. This one is not on maintenance because we are in end of support period, so we have to see if we can replace or not. The SEM is in restrict support period, which means that in principle they don't have problems for PCs because they have a lot of these systems, but just keep that in mind. Okay, and the Origa, we had a contract. We have a maintenance contract, and since last year there was almost no breakdowns, but that's why we had a big breakdown in July or in June, sorry. And since July, it has been out of service. So we have more than 6 months out of service. We have done a lot of things to change parts of the system, but at the end, it turns that we have to exchange the SEM column. The column will come in February. So, and after that, with everything that we have changed and the new column, we think that if we can update the software, basically because it's very old, we can have a system for the next 3 years. Okay, so we kind of brand new system because everything almost is exchanged. The gun is exchanged, the power supplies are exchanged because we have different trials during this time, and now we have this situation. Okay, and the focus ion beam. This is the new system we bought. In 2021. Just remind you that the focus ion beam. We are part of. The basic idea of what we can do is here. So let's say we can watch what we do with the focus ion beam while we are modifying okay, with the ions. There are several options to do because we have the gallium ions with the SEM. We can load up to 6-inch wafer, but then we have some injection system, so local nozzles, which deliver gases locally, which allows us to do local deposition of materials or local etching materials or enhanced etching, because with the focus ion beam we also have enhanced etching. And then as detectors, we include more detectors than we had before. We have, and now we review. Okay, so as a nanopatterning, we have seen what we can do, and I give you a couple of examples because in this case, this is a membrane. Basically, it's a sample with a hole, and then they put a 2D material here, and then we pattern this 2D material so we can align with our SEM and then go with our FIB and make, in that case, these small holes in this 2D material that we measure. Okay, that's for thermal properties. We can, in that case, it's a commercial membrane that they have this arrangement and they need some extra patterns, and we need them because, again, we can align perfectly with SEM and then we can design what we want and so on and so forth. So it's a very flexible tool in this sense because we have the SEM and then we modify the focus ion beam. Because we have, as I mentioned, a gas injection system, we can include these gases here, and this allows us to do, for example, deposition of material like platinum here, or tungsten, or carbon, or TIOS, which is silicon oxide, bad quality versus silicon oxide. And for example, this is very useful to protect the surface before we cut. We have a clean cut, free from artifacts. That's the most basic use. So as a characterization, this is the basic one, which is cutting a material you see inside. We can deposit material just for making contacts, for example. They are not high quality, but they are metallic contacts. Or we can use also for circuit tape. Like this one, where we can make cutting, we can fill parts with oxide, we can reroute with the metal stripes from one part to the other. So all this is possible with the system, okay? And as a characterization, as I mentioned, we put new detectors with the system. One is the EDS detector. And here is an example that it's not only point spectra or mappings. In this case, it's line spectra, okay, which show us the different composition of the materials in this direction, okay, which is in this case. Or we include an STM detector, which basically is a transmission. Scanning transmission electron microscopy means that we have a very thin layer of a material that we can prepare inside, as if you go to the TM, transmission microscopy, but then we have the same detector, but we work at 30 K. Okay, so we can have it on resolution, but we can have quite a good resolution up to the few nanometers. Okay, so that's very good for characterization. And finally, you can do this 3D reconstruction also. As an example, I don't know if it works. It doesn't work. No, no functional. Sorry for that. Maybe we'll show you later the movie. Should check that. The idea here is basically that we are making slices by a slice with a focus ion beam at a known distance, few nanometers, and then we can reconstruct everything in a 3D. I'll show you later, but the idea here is that they wanted, this is a silicon pillar that will appear here. They wanted to see if the membrane of the cell was all around the pillar. Okay, we see that. Okay, and the FIB message again is that we have a very high resolution imaging and patterning. We have a real-time characterization of the process. Almost 10 samples possible. Again, maybe we have to deposit some carbon on top. Of course, because we have gallium ions, these gallium ions will damage our surface. Some of them will get implanted, some of them will redeposit. So you have to keep that in mind when you are making nanostructures. And we have multiple deposits, okay? The current status is that it was installed 2021, so it's still on warranty period, 5 years of warranty period. We had several issues this run-up period. I think that due to the high complexity of the system, it breaks down more than the SEMs. But now we are still at the last month, we are in a more stable situation. So we are happy with that, okay? So that's the focus of IMB. Finally, with the Minatec also, we exchanged the AFM, which also was old, and we had the very old software and some problems with replacement parts. And then, as we needed for the characterization, we bought a new AFM, which is kind of a replacement. Okay, so that's a new system, which is in the same place. Remember that in the AFM, we have basically two ways of working. This is either on contact or by vibrating the tip and slightly touching. We call it tapping mode. Okay, and with that, we have basically topographic information. As these two examples, but we have even phase information. So if we vibrate the samples, due to the material contrast, the phase of the vibration can change. So that in that case, this is a complete plane sample, but it can detect the copolymers. Okay. So as a service, we have this tapping and contact mode service. This new system has higher level of automatization, which means that we can let the sample running also alone, with different sites and locations, and the sample is also optimizing the parameters for the resolution of the images. And finally, this system has the possibility of making many other measurements which are possible with SPM, but of course we are not specialists on that, so we don't offer that as a service, but if somebody's interested, we have to work on that and develop it, and that's also possible. So yeah, as a message, we have ultra high resolution of images, any kind of sample can be imaged. We have 3D imaging. It's a very slow characterization process, but it gives a very high quality. And of course, the resolution always relies on the quality of the sample. Okay, and the situation is that there's some initial bugs working perfectly, so it can be used as a service and as a self-service also. Okay, so now we are reaching the future. And before that, I want you just to share with you some movie, because small movie that I prepared. Because I remember that there was some artificial intelligence meeting, so I want to share with you also my preparation. Maybe you recognize somebody.
Most of us are going somewhere we know. That doesn't mean you should know what to expect. Be careful. Look out for each other. This is the fight of our lives. And we're gonna win. Whatever it takes. Good luck.
See you in a minute.
Okay, if you have seen the movie, you know that they are entering the quantum world, okay, for saving the planet. So now we are also entering to the quantum in a communications project, also to save the planet. Okay. So what we are going to do now is going to see the future. So which is the equipment we are going to buy. In fact, this is something that it's done. It was awarded recently. So we'll see that the laboratory remodeling, which is all ongoing. Some new equipment remodeling that I changed from WC to WC because now it seems that the project is working. And finally, about the people, it's not used. Because about the situation. Okay, before doing that, remember what's next. We are now moving to a new laboratory, as Girona is also improving. So kind of, and we keep the parallels. Okay, that's a new equipment. Okay, we are very happy with that. This is a real DeWalt system for lithography, 100 kV system. The main difference is this is designed for that. It's not an SEM modified. It's designed for that. It can give us higher throughput, higher stability, higher reliability, more automatization than we had before. So we expect that it does have a lot of fun. It has a cassette system, which allows us to load 6-inch wafer, and we will have several cassettes, wafer, chips, and so on. Okay. That was awarded this month, so it means that the tender finished this month. As far as I know, they are signing the contract these days. So, and they have a delivery time of 16 minutes. Okay, so that's the situation. Then, for this equipment, if we see the requirements for installation, they are quite a lot demanding. So basically, they ask for, they want to separate the system for the operator. So when you operate, so they ask for 3 rooms, which means one for the system, one for the service area, and one for the operator. So it means that we need to make a laboratory for the system only. And then they ask also quite strict conditions for temperature. It's like a climate, okay, for the stability of the system. This is basically for the column. It's a very large column, and it changes on temperature and okay. So because we don't fulfill this in our laboratory, we need to make some redesign of the laboratory. Okay, and that's what it's coming. So we have this, and at this moment we are start thinking on this. So the initial proposal is go to this situation, more or less. We'll see how it ends, but this will be where the E-beam is now. Sorry, where the E-beam will be in the future in a closed laboratory. Then we have a wet laboratory for the processing, because we will maybe buy a track for the system also, which is going to put the fiability and quality of the coatings. And then we will remodulate that in order to keep the systems in our laboratory. Okay, so that's it. And the timing for us is as follows. The first thing is that this we expect it to start in January, but it seems that we will start on February because we are already late. Okay, and during the 16 month, the process is that we are in the request for proposal, which means that some engineering company is giving the basic numbers for preparing the tender. So how much will it cost this laboratory remodulation and so on. So that's the initial idea. Then we have to launch a tender. We put here 5 months. It could be more, it could be less. We are told that they will run a lot because they know the importance of the project. Because remember, we are going to save the planet. And then after that, the tender is finished. Some engineering company will have to make the real project. So everything, every detail will have to be described. So that will take a couple of months. All these numbers is because we have talked with the engineering company and they give us. So I'm not just inventing them. Then there is some feedback and then the purchase of the material. And during this period, we will have to move it, okay? Because we have to clean up the area. And the idea is that we will put the SEM somewhere else, so we can keep the SEM capabilities for calculation inside the clean room. We will try to put the AFM also in a new location if possible, and the rest will be moved temporary or definitive, okay, until the finish of the works. For the E-beam, during this time, there is only one alternative that's going to the ICM2, which have a system similar to what we have, so we can go there. And we are agreed on it, okay? Then the works will be executed, and then we will reinstall the new and the old, okay? And the systems that will not be reinstalled or up to site are those, okay? Basically, because it will be out of service already, and not support, and they are. Okay, then equipment renewal. Then the first one is we have these 2 SEMs. As I mentioned, one is already out of service with end of support, and this one is in the strict mode. And the idea is that with the per chip, we are. It seems that we are going to buy it. Okay. Then for this new one, the idea is we want a system for characterization in the clean room, so it has to be CMOS and not CMOS. And we will also add some EDX capabilities because we think that will be useful in the clean room also. But any other idea is welcome because this still has to be defined. Okay. Then for the right 150. This is a system that, as I mentioned, we are in also quite a critical situation. For the lithography, we have a replacement, so in principle, we don't have to look for that. But for the capabilities for the people for reverse, for metrology, we don't have all that. Okay, and that's something that we have to do. And it seems also that the PERT chip is going to provide some funds for replace or the system or similar system which provides this capability. Okay, so that's also something we will discuss and we will share with you and invite you if you are interested. Okay, so that's also good news. Finally, regarding the nano-imprint activities, as I mentioned, we have this system which is unused since 2020, so now it's completely abandoned and needs to be serviced if needed. And then we have this nano-imprint which is still working, but it is a minimum. In fact, we are only providing service to some external users, which is basically to the student which nobody in the house is using. So our main idea at this moment, if nobody complains or thinks differently, is that we keep the current situation, it's keep it running until the system. Okay? And then if nobody is interested in this activity, we allow this. Okay, so that's a main thing. There are alternatives on the campus. There are few places where you can still possible. Okay. And more or less that's it, because about the people, we are 3 people, and we expect to be fulfilling the 3 people. Okay? So thank you for your attention. Thank you for all the images from all these collaborators. And that's it. If you have questions, now it's time.
So yeah, we can just say that the idea of this talk is to try to have an open discussion now. Any comments, it's really welcome, because many things are open. But okay, so comment questions, obviously afterward we can talk. Right.
We need to prepare something for when the owner plays the channel.
We will. Yeah,
I have a question, like for the part where they will be changing the clean room, what are we supposed to do? Are we gonna have any other facilities, or we just wait?
In principle, it's supposed to be between 2 and 3 months, the execution of the works. And as I mentioned, for the SEM and for the AFM, we'll have some location. Since
the SEM, we're quite sure where to locate it.
For the optical microscope, any table anywhere can work, but for the processing or for spinning, basically, that's what I understood. There is Marta with the microsystem lab. I don't have any other. We don't have any other option. If it's possible, the spinner can be reinstalled somewhere. No.
So the closing of the Nano is expected
In 1 year.
So between this January to we will remove the tool just before Christmas,
Yeah.
more or less.
Yeah, that's it. And everything goes smooth.
Yeah, that's a plan.
Yes.
And then we close January to March 2025. And everything goes smooth. And many other things will occur in Finland.
Yeah, maybe even when we mentioned that the SEM will be reinstalled, maybe we have the new SEM here. Since then we can start the processing for SEM. Install and yeah.
And isn't it possible to make these, for example, in summer? Because anyway, if it's 2-3 months, maybe it's.
Now the tool will arrive.
The tool will arrive when it arrives.
Yeah.
And we have to be ready when it arrives. So we cannot change the timings for that because the tender has to be executed, the works has to be executed. So
In the project to see the funding is end.
I have to say that the initial idea was to make that in summer because we launched the tender in June last year or even before, but it took 6 months to solve the tender. Okay, so more than 6 months.
Maybe there's a delay. Maybe there's a delay and then we will go to the summer.
Maybe there's some delay. In fact, the contract is not signed yet, so maybe not.
Would you expect that with the new beam, the rules for some surveys or cannot be maintained as open as it is now?
We think that it has to be open to self-service, but we have to be sure that the people is not. I don't see all the people.
I don't know how much you want to be precise in your planning, but you are planning to buy material in December?
No, not me.
Oh.
That's
Okay.
so that's the company that will make the works.
Okay, not from the CNN.
No,
Okay,
no.
okay. See, December is the worst month by something.
In fact, I didn't mention exactly, but as you see in the planning, the remodeling of the laboratory includes also new weight benches, new spinners, all these. But all these we try to include on the tender, so it's commerce de poids en main. So that we don't have to make more tender or more anything, so that's it. We'll see if we succeed.
Right now, there's not a, right? It's not ours, I think.
Okay. In the clean room, there are 3 nanoimprints. One is the MPS, which is out of service since 2020. The other one is the one that I showed, and there is a 2-inch system, which, as I remember, minimum 6 or 7 years and nobody touched. Okay, and it doesn't belong to us. It's from ICN2, from a researcher that it's not in the SN2 now. So it's a kind of model. So when we need space, we don't. I mean, we talk with the people in ICN, and I think they don't. Because we even don't know the password to switch it off. Switch it off since many years. So.
¿Luego de qué? ¿Dónde está el logo? Ah, sí.
Any more questions? Maybe online.
There's one. No, there's nothing. No, there's one question.
The movie, really easy. This is free software, so it's online.
Okay, there are 2 questions. Jad says, thanks, Xavier, for the nice presentation. Once we have the new EBL for one level full 4 inches wafer, what is the range of time that we can manage per wafer?
That depends on what you do in the wafer. That's not there is no answer for that. I mean, I expect that, for example, the wafer we did here with the nanowires, which took a weekend to make it, that's probably made in a few hours, 2 hours maybe. Yeah. So that's the range that we are talking on change on productivity. Okay.
Okay. And Inigo says, please explain if the renewal of your area will affect the other areas in the clean room.
Okay. In principle, we are not going to affect the other areas. Okay. Maybe at some point, because maybe they have to cut some service and yeah, maybe they have to do that. We will see that.
Maybe photo.
Yeah, maybe.
MLC, because they share the same air conditioning systems, and we have to remodel this air conditioning system. Actually, we make an improvement. So there will be some implications.
Yeah.
But
we will try to keep a
short
short
at the same time. So we have 2-3 years, complicated years in front of us, but we will manage it as best as we can.
And also, we are sharing some service area where there are the water supplies and some supplies that maybe at some point you'll have to, maybe 1 day, 2 days, one day, cut it and make it for you. But that's the idea is this. Okay.
Okay, thank you.
I mean, you mentioned that it needs a very stable.
Yeah. We will make a new climate system specifically for the E-beam and for the rest of the laboratory. So it will be kind of, and we have also a cancellation system for magnetic and DC fields. Also because we are out of specs for that also. So we need that.
Any other questions?
The electron beam will be in the steel ICN provisional.
Which one? The one, this one? No. This we will.
Not this one. The
The old one. Yeah, no, the one we will throw it away. That's the idea. What I mentioned is that in that, so in ICN, they bought a system which is similar to what we have now. Similar. It's kind of the same. We share the software. They have also an interferometric stage. So what we can do now here, we can do it also in ICN. Okay? And we agreed with them that during this period, if we need to go there, we can go. Okay.
Thank you very much.
Okay.